Welcome everybody. My name is Borbála Pap. I'm an assistant professor on the Department of Structural Engineering of Budapest University of Technology and Economics. I will present you my research, which will be the human-induced vibration of long rectangular steel and composite floors. In case of lightweight, steel-framed or rip-stiffened floors, vibration control can play a major role in design. The accelerations due to human activity, like for example walking or running, can be rather high and can cause human discomfort. Therefore, there are several design guides and design rules which contain the analysis for human-induced vibrations. The easiest way, of course, to just check the first eigenfrequency of the floor. And in some cases, if it's bigger than a given limit value, we don't need to deal with further vibrations. However, in cases when we are under this limit value, or the floor is used for sport activities or some other type of special activities, we need to check the accelerations. And of course, these accelerations have to be smaller than a given limit value. In the dynamic evaluation, usually, we treat low-frequency floors and high-frequency floors differently. In case of high-frequency floors, we usually check the calculations, check the accelerations for an impulse load. However, for low-frequency floors, we calculate the accelerations for a harmonic loading. In this presentation, in this research, we only dealt with low-frequency floors, therefore with harmonic loading. Of course, there are several suggestions in the literature how we can calculate floors, long floors, and how we can calculate these maximum accelerations which can occur. Here you can see that first of all we need to calculate an effective width, which will basically give us a beam, which will be the portion of this floor. From this beam we can of course calculate the modal mass, and with the help of that modal mass and the maximum magnification factor of a single degree of freedom system, we can calculate our acceleration, maximum acceleration in the resonant point. However, this given effective width has no physical background, or this physical background is not clear. Our goal was to check the actual physical behavior of long floors and according to that calculate their response, their acceleration. In our analysis, we investigated long floors, as I mentioned, and in these cases there's an extra energy dissipation in the system because of the so-called radiation damping. It's basically caused by the wave propagation to infinity, and it's very important to say that in case of rip-stiffened orthotropic floors, a slab with a side ratio 1:1 can also be long, mechanically long. Two cases were investigated to give our formulae. First, for a half sine load, we made an analytic solution, and for a concentrated load, we made a numerical solution. According to that, we try to give a formula for the effective width and for the dynamic magnification factor, and we compare them to the formulae given in the literature, in the current design codes. First, I will present our analytic solution for this half sine loading. Here you can see the differential equation of a simple orthotropic plate, which can be simplified by the Levy solution. Here it can be noticed that if we set this theta value to 0, we will exactly get back the differential equation of a beam on elastic support. Or if we set our D11 stiffness value to 0, then we will get back the results of an axially constrained bar. So first we derived the solution of these simple cases when they are infinitely long and convert them to a simple SDOF system. As we know, in case of an SDOF system with Xi structural damping, the maximum of the amplification factor at the resonance point is 1/2 Xi. And as we know, before and after the resonance point, the phase angle is 0 or 180 degrees. However, in the infinitely long beam and in the infinitely long bar, we have a much higher energy dissipation. In case of an infinitely long axially constrained bar, the phase angle after the resonance frequency, which can be in these cases called cutoff frequency, is 90 degrees, which is basically equal to an energy dissipation of a dashpot mass system. Also, the maximum amplitudes are lower because of the same phenomena. In case of beams on elastic foundation, it's 1/2 Xi on the 0.75, and in case of axially constrained bars, it's 1/2 Xi on the power of 0.5, which, as we can see, are much different than in case of a single degree of freedom system. After that, we also derived the magnification factors at the resonance point for different type of long floors. As I mentioned, if the plate has no torsional stiffness, we basically got back a beam on elastic foundation. So this maximum amplification factor will be 1/2 Xi on the power of 0.75, just as before. We also checked another case, the Huber orthotropic plates. In this case, this amplification factor, the maximum value in the resonance point, is approximately can be calculated with this given formula. Here you can see a diagram which shows the exact value of the maximum amplification factor in the resonance point in the function of the side ratios. However, the side ratios are also normalized with the ratio of stiffnesses. As we can see that the given formulas here, showed with a red line, can be used approximately from the ratio of 5 to 10. We performed more numerical examples. Here I would like only show one. We were examining the floors of a new campus of the University of Physical Education. These were huge reinforced concrete floors with steel beams. Here the longer side of the floor is 95.7 meters, the shorter is 54.8 meters, so the side ratio is 1.74. However, if we normalize it with the stiffnesses in the two direction, this ratio will be 8.44, so basically we are here in this diagram, which I also showed you in the previous slide. Here you can also see the amplitude and the phase angle of this floor if one person is jumping in the middle of the floor. The maximum value of the amplification factor is 10.3, and the same value with our approximation formula would be 11. So we are much closer to this value than the value given by an SDOF system, which is basically more than the double of the reality. Finally, we compared the different solutions to each other. Here you can see several diagrams which show the value of the maximum amplification factor in the resonance point in the function of the side ratios, of these normalized side ratios. The continuous line is the exact solution, and the dashed line is the design formula given by the current design codes. And we also show the results of our formulae for long floors by dotted lines. The different diagrams are for different damping ratios and plates with no torsional stiffness, and for Huber orthotropic plates. As we can see, when we have a plate with no torsional stiffness and the structural damping is 2%, the response calculated by the design guide with dashed line, so with the shown effective width and the amplification factor of a single degree of freedom system, is practically the same as the exact solution. However, these two values, the effective width and using the amplification factor of a singular degree of freedom system in case of a long floor, has no physical meaning, have no physical background. And of course, for different damping ratios and for different type of plates, this value from the literature and the exact solution are not even close to each other. They will give high errors. Additionally, these suggestions in the design code are only good for the resonance point. So away from the resonance point, even in this case, we have high errors. So, as we have seen, rectangular orthotropic floors with realistic dimensions may behave in a significantly different manner than single degree of freedom structures. The amplification factor in the resonance point is much lower than what we use in case of SDOF systems, which is actually caused by the so-called radiation damping. According to an exact and a numerical solution, we derived approximate formulae for the maximum of the amplification factor and also for the effective width, which we can use for long floors. And the advantage of this formulae that they also contain the physical background, the physical understanding of the phenomenon. And thank you for your attention.